Everybody, that for the last session of the day, we'll have an informal question and answer session with today's speakers here. And as for the last formal talk of the day, we have Pierre Colmez from the École Polytechnique, who will speak about the p-adic local Langlands correspondence for GL2.
Yes, as usual. Okay, so thank you for the introduction. So in this talk, L is going to be a finite extension of QP. And it will be the field of coefficients of every object that we are going to consider. Do you hear something? Yeah? Okay. Yeah, so from this, we construct some rings called R, which contains E dagger containing E. So this one is called the row bar ring, and it is the ring of analytic function on a so each function is converging on some annulus. So this is radius 1, and this depends on the function. So here is 1. The outside circle is radius 1, and this radius here depends on the function. And E dagger is just a set of analytic functions on this kind of thing, but which are bounded. So here it's bounded. And this one is a completion of that one. I mean, now that you have bounded function, you have a natural norm on it, and you just complete. And this one you can also define in the following way. So you start with something I call OE plus, which is OL double bracket T. Then you invert T, you get OE. One over T, and then you complete for the p-adic topology, and you get this one, and E you just get it by inverting P. So E equals OE of 1 over P. Okay, so actually these two are fields. This one is some kind of Bezout ring, which is the closest you can hope to a principal ideal domain. There, and so something that will be quite useful to have in mind for the rest of the talk is what these rings look like topologically. So in fact, you have exact sequences like that due to Amis, let's say. So this, by this, I mean continuous functions on ZP with value in L. By this, I mean continuous dual. So this is the algebra of measures on ZP. And this is isomorphic to OE plus 1 over P, naturally. So going to E, going to continuous function over ZP. And you have same thing with R. So R is an extension of the locally analytic function over ZP. So LA means locally analytic over ZP. And it's dual. So this is a space of distribution. Okay. So to each of these rings correspond a theory of phi gamma modules. So maybe, yeah. So phi gamma modules so basically it's a module over any of these rings together with action of phi. Gamma is the same thing as ZP star. Is in fact the Galois group of the cyclotomic extension of QP, but it will be CP star. But it is better to view this as a module with an action of this following monoid, ZP minus 0, ZP 0, 1. And so the dictionary goes as follows. So phi is going to correspond to P001. Here, if you have an element A in ZP star, it's going to correspond to A001. So A in ZP star. And finally, here you have a T. So 1 plus T here corresponds to 1101. And then you have Fontaine's equivalence of categories that we are going to use. So if you start, so V will always stand for a representation of the absolute Galois group of QP. So here you have representation, L representation of GQP. So GQP is the absolute Galois group over E. And this is an equivalence of category with phi gamma modules over E. And here you have a D corresponding to a V. So this is the equivalence of category of Fontaine. So I'm not going to explain how it works. But anyway, what you have to know is that you can, for everything concerning Galois representation of GQP, you can replace Galois representation by phi gamma modules. And these phi gamma modules are objects which are much easier to handle. What? Yeah, sorry. And you have to add étal somewhere. So étal means that the Frobenius is of slope 0. So its eigenvalues are units, have valuation 0. And then you have the same thing, but over E-dag. And here you call it D-dag. And the same thing over R. And here you call it D-rig. OK, so let me just give you the relationships. So, of course, what you have is that D is E tensor E-dag D-dag. And D-rig is R tensor E-dag D-dag. So D-dag is the smallest thing, and it is the one that allows you to go from a D, which Fontaine provides, to a D-rig, which is over the Roba ring, which is a ring over which you can define many, many new objects. And so it is very easy to go from D-dag to D and from D-dag to D-rig. It's very difficult to go to in the other direction. So here, going in this other direction, this is due to Charbonnier and myself. And here, this is due to Kedlaya. And probably the most difficult theorem in the whole theory is Kedlaya's theorem that allows you to do that. OK. So that's one thing. And now I want to explain to you how to associate to certain Galois representation of GL2 of QP. So the theorem is the following. So you take a V, which is, well, V or a D, let's say D, which is going to be irreducible of dimension or rank, the same because we have a field of rank 2 over E. And to this D, I want to associate a pi, which is going to be a representation of GL2 of QP. So, to which I can associate a delta D, which goes from QP star to OL star. So it's a character from QP star to OL star. And this delta D is defined by delta D of x is x norm x to the minus 1 times determinant of D. So what do I mean by that? So determinant of D is something of rank 1. So it corresponds to a Galois representation of GQ through this dictionary. And so to this Galois representation of GQ, you can attach a character of QP star using local class field theory. And so this local class field theory is going to match this character here to the cyclotomic character. Okay, so that corresponds to the cyclotomic character. Okay, so you have this, and then what you can do, well, you define, so we define, you start from a irreducible rank 2 phi gamma module over E, and you can attach to it something that I call D cross P1, together with an action of GL2 of QP. And you also attach to it a pi, which is a pi depending on D, and plus other things. So from this D cross Q pi1, sorry, you have also maps, restriction to U, going from D cross P1 to D cross U for any U which is an open compact subset of QP. Of QP or even of pi1 of QP. So this pi1 is pi1 of QP here. Okay, I just write pi1. Well, I will maybe say it's some kind of sheaf on pi1 of QP with values in I don't know exactly what. So, but but I mean this is supposed to be more or less the sections over U and things like that. Okay, and you have an action of P1 on of GL2 of QP on P1. It's the usual action, and so I mean the rules are the following: that the restriction. So D cross ZP is going to be our D, our starting D. So the section over ZP are exactly D, okay? And then, yeah, so what do I want to say? Yeah, maybe there is one last thing I did not define here. So if you have a phi gamma module étal, you also have a psi going from D to D, which is a left inverse. So psi is a left inverse to Frobenius. And morally, this phi circle psi is a restriction to PZP. So you have all these things, and now, so the theorem is the following. So you have exact sequence like that. 0 goes to this pi dual, twisted by this character delta D, goes to D cross P1, goes to pi, goes to 0. And everything comes with an action of GL2 of QP. And inside, you have something called D-dag cross P1, whose image are going to be the locally analytic vectors of pi. So I'm going to define what this means. And here you still have pi star cross delta D. And once you have done that, you can extend from D-dag to D-rig and get an object like that. So you still get to P-an, goes to 0. And now you have the dual of locally analytic vectors in the kernel. OK, so here you have equality. Here you have, you have inclusion in this way. Here you have inclusion, locally analytic, and here you have equality. OK, so what I want to point out is that these exact sequences should remind you of the exact sequences I wrote here. Okay. And in which way? So what kind of object do I have here? So this pi, I said that it was a representation of GL2 of QP. So it's what is called is a unitary admissible representation of GL2 of QP. So unitary means the following. It means that you have an action of a continuous action of GL2 of QP on some p-adic Banach space, so L Banach space. And unitary means that there is a lattice which is invariant under the action of GL2 of QP. So that's unitary. Admissible is some finiteness condition, so it is in the sense of Schneider and Teitelbaum. But here it means that when you reduce this lattice modulo p, you have something which is of finite length over GL2 of QP as the OL of GL2 of QP module. So it's a theorem of Martel and Livnet that this implies admissibility in the sense of Schneider and Teitelbaum. So let me go on. So P-an here is a set of locally analytic vector. So it's a set of V in pi such that when you look at the function G maps to lambda G times V, so this is analytic, so locally analytic on GL2 of QP for all lambda in the dual. So Schneider and Teitelbaum proved that if you start from any representation, not only of GL2 of QP, but of GLN of QP, for example, then you will always have locally analytic vectors. So this space, you know beforehand that is never going to be 0. And then let me introduce something that will be our main object of study, the space of locally algebraic vectors, so p-alg, so it's locally algebraic vector. So the same definition, except that you ask that it is locally polynomial in the entries of the matrix. So in A, B, C, D. So this is the entries of G and the determinant, AD minus BC to the minus 1. Okay. And then finally, to give you an idea of how you can represent this kind of object. So you have, I told you that this is some kind of sheaf over P1. Just means that no. Locally, it's really a polynomial in A, B, C, D, and AD minus BC. So it's I mean, this is the algebraic functions over G, if you consider G as an algebraic group. Yes. But this should be true locally. I mean, you can multiply by a locally constant function. Okay. Yeah, and so now if you have a Z in D cross P1, what you can do, you can associate to it two things. You can associate to it Z1, Z2, which is going to be the restriction to ZP star to ZP of Z1, and the restriction to ZP of Z. And then W of Z, W is 0, 1, 1, 0, Z. Okay, and you get two elements of D because of what I said here. And now, because P1 is just the glue obtained by gluing two copies of ZP along ZP star, then these two Z1 and Z2 have a condition. I mean, they are not completely unrelated. The restriction to ZP star should match. And the condition is that when you look at the restriction to ZP star of Z2, then this should be the action of 0, 1, 1, 0 on the restriction to ZP star of Z1. Okay. So basically, what you have here is a description and in terms of Z1 and of D cross D with some condition of some compatibility condition on ZP star. And now I should make some comments.
Sorry, before you make comments, what is the theorem?
So the theorem is that there exists a construction that gives you, starting from any D, a pi with all these properties.
That's the end of the theorem.
Well, that's there is no real hand. I mean, everything is part of the theorem. So the part of the theorem is this, which is part of the construction. Okay. So let me make a remark about how this theorem is proved and what you have actually. So, some remarks is that so the formulas for the actions of GL2 of QP are really horrible, and you cannot use them. So, and useless. Yeah, so I can tell you where they come from. So they come from the following thing. So if D is going to be OE plus, well, OE plus disappeared, but I told you that this was the same thing as the measure, or even E plus, as the measures on ZP. So OE plus was with value in OL. So this is OL double bracket T. Okay. So if you start from this one, this D, and you apply, if you look at the formulas you use, in fact, what you get, your D cross P1 is the measure. So you take the continuous function on P1, and you take the dual of that, and on it you have a natural action of GL2 of QP because you have a natural action of GL2 of QP here. And the formula I wrote are exactly modeled on the formula you get here, except for one thing, except that you only have the right to use things coming from Phi gamma modules. Okay? And so you have to translate usual formula on P1. So you have, I mean, if you have something, if you have a measure on P1 and you want to define something like the integral of phi of ax plus b over cx plus d mu, okay, what you do, well, you cut everything into small pieces, and then you take a limit process. Okay, so cutting things into little pieces you can do by using phi and psi like this. And taking a limit process you can do, you just take a limit process. And in this way you get horrible formulas. And you cannot use them, okay? So, but the only thing something which is not horrible is that the action of this mirabolic subgroup this you can actually read directly on the without taking limits. So it's easy to describe. So the theorem is the following now. You start from this space. You look at the formula you have for this action. You can twist it by the character delta d. In fact, I put here delta d of cx plus d. Then you get formulas. You write them down, and you see that they have a meaning for any phi gamma module. And then this gives you the d cross p1. And then what is not completely, so what is surprising is that this process works for any phi gamma module, any character, delta, which is a very, very bad sign because it would mean that you can attach to any Galois representation of any dimension and any character, you can attach a representation of GL2 of QP, which is very, very bad. You don't want that. So you are saved by the fact that usually you're not going to have a splitting in this way. Okay? So the object you would get here will be defined every time, but it will remain as it is. It will not be an extension of something which is a Banach by something which is a dual of a Banach, and both being invariant by GL2 of QP. So, which means that there is no contradiction at this point. Yeah. So is that? So it's about everything I want to say about the construction. Yeah, and so I should also say that not only these formulas are useless, but at some point, when you want to prove that this theorem is correct, so meaning that you want to prove that you really have something inside which is stable under GL2 of QP, you cannot prove it directly. At least I cannot prove it directly. So the way it works is that first I use the fact that I know many, many, many cases in which this is true. And then I can prove it by analytic continuation. So not only it is useless, but you cannot get a handle on them. So, so anyway, so what we are going to be interested in is this locally algebraic vectors. So if you assume that this theorem exists, now we are in the following situation. I remove it. So you have, instead of having a correspondence, you have some kind of triangle here. You have Galois representation to which you can associate a phi gamma module, and to which you can associate a representation of GL2 of QP like this. Okay? And this triangle is quite useful. Okay, so let's go to locally algebraic vectors. So what can you say about locally algebraic vectors? Yeah, I should point out also that all these formula are easy except the formula describing the action of 0, 1, 1, 0 on ZP star. So that's basically the one you cannot get a handle on. Okay, so as I said, the action of the mirabellic subgroup can be read easily. By easily, I mean that you don't have any limit process, so you just have, algebraic formulas. And because of that, you can prove the following statement. So a theorem about these locally algebraic vectors. So the first thing is that if p-alg is non-zero, then V, which is over there, is Hodge state with Hodge state weights distinct. So H state weights, so weights So they are distinct. So let's call them A big less than B. So that's the first thing. The second thing is that you can actually relate this, describe these locally algebraic vectors in terms of the weights up to a certain point. So p-alg, you can write it in the following way. PLC, so LC stands for locally constant or smooth, as you prefer. Tensor, some algebraic representation. So this algebraic representation is determinant to the power A. Tensor, the determinant, the symmetric B minus A minus 1 power of the usual action of GL2 of QP. So you have an action. And here you see that you better have the Hochstate weight to be distinct, otherwise you would not know what to put here. Excuse me? L square? Well, I just want to call it QP square, maybe. Yes. So moreover, so you get this factorization, and this pi LC is irreducible, except in one case, except if your representation V is crystalline up to a twist, crystalline, and crystalline with, so you have two values of Frobenius on the decrease of this representation, and these values are related by the following recipe, so with eigenvalues of Frobenius, which will be alpha and p alpha. So what happened in that case is that, so associated to this, you have a representation of the Veil-Delin group. And because of this relation here, you could choose to put n non-zero and get still an action of the Veil-Delin group. And so when n is non-zero, you have something which is semi-stable but not crystalline. If n equals 0, you get something crystalline. And in this case, what you find is that this pi LC is up to twist. Again, you have an exact sequence like this. So you have the Steinberg representation, goes to pi LC, goes to the trivial representation, goes to 0. Okay. Well, no. Right here. And then the last thing is that you can. Excuse me?
What's the definition of
Steinberg is going to be locally constant function on pi 1 modulo the constant. Okay, so the constants that you mod out, you find them here. And so, in fact, this representation is induced of a character. It's you have two situations where this induced representation of a character is non-reducible, and that's one of them. The other one is the Steinberg. So in fact, I find it quite striking. So what happens is that in the case where you have an n non-zero, what you get is only the Steinberg. You don't get the 1. And then the last thing you can do is actually prove. So in that case, you can prove that this pi LC is what you get from the usual local Langlands correspondence when you apply it to the dPST of V. Well, this if V is becomes semi-stable over an abelian extension of QP. So these are the cases where the representation you get here is going to be some representation from the principal series. So that's the case where everything is very easy to describe, and you can describe everything just looking at the action of the mirabolic subgroup. But that's not what you want. So the real theorem is the following. The theorem, and I will try to explain to you how you can go around the fact that you cannot use the formulas to prove anything. So the theorem is the following. So first, p-alg is non-zero if and only if V is the RAM, or potentially semi-stable is the same. Well, let's say the RAM is shorter. The RAM with odd state weight less distinct. So the RAM is stronger than odd state. This is supposed to cover only representation coming from geometry, more or less. And the second thing is that in all cases, this statement is true, is that pi LC. So because you are the RAM, you are in this situation, and this pi LC is going to be what you get by the usual local Langlands correspondence associated to the dPST of V. So I will explain to you how you prove that. And I should say first that this second statement has application to global problems. To Fontaine-Mazer. So that's work of Emerton and of Kizin. And also to prove that, I use the result of Emerton. So it goes both ways. I mean, by using this result, Emerton is able to prove many cases of Fontaine-Mazer, and by using result of Emerton, I can I can use that. So.
Sorry, and what do you expect? I mean, you have that this condition too. In what generality should it fall? So
Which one? But that's a complete generality.
yeah, but
So this theorem is that you have all locally algebraic vector if and only if your representation is the RAB with distinct weights. Okay, so you know, and if you have a representation which is the RAM, you can associate to it a dPST of V, which is a representation of the Veil-Deligne group of QP. And by the usual local Langlands correspondence, you can associate to it a representation of GL2 of QP. And this theorem tells you that it's exactly what you want.
yeah, but you get a different assumption in 3.
Yeah, because here I was just explaining to you what you can prove without having to
I see.
to how do you say to plunge your hands into something very dirty. so now I mean, if you want to prove that, you have to do something a little bit complicated. So I will try to explain to you what you can do to get around the fact. I mean, the main problem is that you can write down these formulas, but you can really not use them. I mean, they don't converge at all at a rate that you can use to prove anything. So how do you go around that? So there is something which I found extremely useful. So you look at this picture here, and then you have a corresponding picture when you take here psi equals 1. Here you take the dual pi star, and you look at elements which are fixed under P001. And here you look at something which I call the Iwasawa cohomology of V. And what is this Iwasawa cohomology of V? It's something that everybody here studies, more or less. So it is H1 of the absolute Gara group of GQP with value in OL double bracket gamma. So gamma is the Gara group of the saxotomic extension. So it's P star tensor V. So if you prefer, you can also take projective limits of under co-restriction maps. And so what happens is that you have natural isomorphism here. And so this isomorphism here is due to Fontaine, in fact. And so it's a description of this Galois cohomology in terms of phi gamma module. And in fact, this isomorphism is something that you can view as local factors for p-adic L functions. So by which I mean the following. So there is a big machine due to Perariu to produce p-adic L functions out of element of global elements like this. Instead of having GQP here, you have GQ. And this machine uses this isomorphism here. So you can view it really as some kind of local factors for p-adic L functions. And on the other hand, it's absolutely...
What are the factors of epsilon?
It's everything together, local factors. And here, so the map is just if you have an element Z in the dual, you associate to it the restriction to Zp star of Z, to Zp of Z, and you get an isomorphism between this and this. Okay, so now that you know that, what you can prove is the following. So as I told you, the main problem is to describe the action of P of 0, 1, 1, 0, which is W on D cross Dp star. And how do you get around the fact that you cannot really use it? Well, you use this map here, and you define something that Fontaine calls the heart of the phi gamma module. So it's called C, which is 1 minus phi d psi equals 1. So it's more or less d psi equals 1. You can differ from it just by a finite dimensional thing. So it's also the same thing as the restriction to Zp star of d psi equals 1. So it's 1 minus phi or something like this. It's just restriction to Zp star. And you define C prime to be the same thing with 1 minus delta D of P minus 1 phi d psi equals delta D of P minus 1. And so what you can prove by using this identity here is that, in fact, you have W. So W is this of C, which is equal to C prime. So why is this good? So what you have to know is that this C and C prime, they are well-behaved things. And you can use them to reconstruct the entire D cross Dp star. And more precisely, you have the following result of Fontaine also. So the result of Fontaine is the following. So you take any phi gamma module over E now, and so you have a C like this, so C of D. So the first thing that Fontaine proved is that C of D is an so OL double bracket gamma module. So because I am over E, I have to invert P module free of rank D, where D is the dimension of big D over E. So that's one thing he proved. And the second thing, so if you use this and you use idea for coming from Iwasawa theory, then you can actually build up a pairing on this kind of thing, and then you can also give some formulas that involve only phi gamma modules. But so what I'm going to say is the following. So there is some pairing going from C of D cross C of D check. So this check here is the Tate dual of this D. So if D corresponds to V, this check is going to correspond to ohm of V in twisted by 1. Going to lambda, so this I call lambda. And this pairing, so this comes from Iwasawa theory. It comes from H1 Iwasawa of V cross H1 Iwasawa of V check to lambda. This pairing is linear with respect to the second variable. So you have Z1 sigma A or gamma Z2 equals Z1, sorry, gamma of Z1 Z2. But it is antilinear with respect to the first one. So gamma Z1 Z2 is equal to gamma minus 1 Z1 Z2. And finally, what Fontaine proved also, or maybe it's in her thesis, is that if you look at this D cross ZP star, well, you can reconstruct it from this C in the following way. Well, this is just, so OE, or E of gamma, tensor over lambda C. And what do I mean by E of gamma? So here I have a group that looks a lot like ZP. So I take a generator, gamma, and then I replace everywhere where I have T in the construction of E, I replace it by gamma minus 1. So it means that I have to invert gamma minus 1, prove that gamma minus 1 is invertible over this thing, and that you can actually write this thing. So that's why it's important to know what W does on C, okay? Because C is big enough to be able to tell you everything you need about this module here. And so the upshot of everything, so what do you get now? So, I mean, motivated by the fact that you're supposed to have a link with p-adic function, and these p-adic functions are supposed to have some functional equation, then you prove something which is called the explicit reciprocity law. And explicit reciprocity law are everywhere in the theory of p-adic functions. And this explicit reciprocity law tells you the following. So explicit reciprocity law, which is going to be the following. So if you look at Z1, Z2 Iwasawa, so you get an element of lambda. Okay, lambda. So maybe I should tell you that if I have a mu in lambda, I can send it to OE by just looking at integral over ZP star. So lambda is, or gamma, of 1 plus t to the chi of gamma mu. And this is going to be now an element of E plus. So because I have an element of E plus, I can take its differential. And now I get an element of E plus times dt, or dt over 1 over t. And the formula is the following. So it is something like W star Z1 cross Z2, where where this now is defined only in terms of phi gamma modules. And it is as usual. I mean, what I'm doing is just, if you start from two measures, what you get is the following thing. Integral over Zp star of phi of x mu1, mu2. Imagine that your phi gamma modules was E plus. What you would get is the following Mellin transform, integral over Zp star cross Zp star of phi of x minus 1 y, mu1 of x, mu2 of y. Okay, so I can give you also horrible formulas for this in terms of phi gamma modules. You have to cut everything into small pieces and take a limit. But basically, what it tells you is that you can compute these things that comes from Iwasawa theory, Galois cohomology, purely in terms of phi gamma module. And the upshot of everything is the following.
What's the D?
D is just differential. So, I mean, df is what you think. So it is going to belong to E plus dt. In fact, it's better to put E plus over 1 over t. Okay. And here, so what? Yeah. So maybe I should say that d check is a hom from d into E times dt over 1 plus t. I mean, it's a one way to say to describe the Tate dual. So that you have a residue map. Okay, so what happens in dimension 2 is the following.
So where is the dt on the right-hand side of the formula?
On the right-hand side, it's here. It's because you have something that pairs something with an element of d check, and here an element of d. Okay, and so you land here. So anyway, what is very important for dealing with locally algebraic vectors is the following consequence. So if you are in dimension 2, then d check is the same thing as d, where you twist by this character minus 1. Okay, and so you can look at this pairing, this Iwasawa pairing, W of Z1, tensor delta D minus 1, so you get an element of D check. You pair it with something Z2, Iwasawa, and the consequence of what is that this is bilinear, so it's E of gamma bilinear. And what is very important, it is anti-symmetric. So that's very, very important. It means that if you have a line, you know where the line is going to be because of the anti-symmetry. So here you have W. This W is 0, 0, 1. Or maybe I put it again. You don't know exactly. I mean, you cannot describe this image, but you know in which line it's going to land. That's why this anti-symmetry is very important. Okay, so how do you apply this to locally algebraic vectors? So if you want to find locally algebraic vectors, you have to find. So you look for subsets or submodules of D rig cross P1, which are stable under under GL2 of QP. So the main problem is to find things on ZP star which are stable by W. And so now let's look at D, which is odd state. So with weight 0 and k, and this k is going to be b minus a minus 1. So you can always assume that the weights are 0 and k by twisting by a character. Twisting by a character makes no difference. And then you have the following thing. So this implies that if you look at Biederam tensor V, so V is a Galois representation corresponding to D, so it contains two vectors.
K is just b minus a.
What?
A will just be b minus a.
K, B minus A.
You had a and b, and now you.
Yes. So B theorem contains two vectors E1 and E2 with the following properties. So gamma, so G of E1 is E1 for all G in GQP. So that's because you have odd state weight 0 here. And the second thing is more subtle. So G of E2 is going to be E2 plus epsilon log of the cyclotomic character of G times E1 with this epsilon equals 0 if Durham and 1 if not. So that's how you can make the difference between a representation which is Durham or not. When you tensor with B Durham, you get this kind of thing. And then, so that's what we are going to use to prove that, for example, you don't have locally algebraic vectors in case you are odd state but not Durham. So then what you do, well, you define something that should be this thing which is stable under GL2 of QP, this submodule. So you define it in this way. So you define some module n rig, which are going to be the z in t minus k d rig. So this t is Fontaine's t. So t is log of 1 plus t, and this is Fontaine's t, 2 pi I. So you look at the z in t minus k d rig such that phi minus n of z belongs to, so you take L, you add p to the nth root of unity, double bracket t, tensor d Durham. Well, maybe not d Durham, but the thing generated by E1 and E2 for all n big enough. So what you prove is that this n rig contains d rig, and which contains t to the k d rig, and you have that n rig modulo d rig is isomorphic to r mod t to the k, and which is isomorphic to n rig, g rig mod t to the k n rig. Okay, once you have done that, you are going to define two subsets of this C.
You mean d rig contains t to the k n rig?
D rig, n rig mod d rig.
T to the k. The left hand.
Oh, sorry, r mod t to the k, yes.
But move to the left as well.
D rig mod t to the k n rig, so that's okay. Sorry, n rig. Okay, and so now you have a second thing that comes from Iwasawa theory, which is the following. So you take some C alpha rig, which is going to be 1 minus alpha phi d rig psi equals alpha. So, I mean, previously I introduced C without a rig and no alpha. So here alpha is any element of OL star. And I will also use a beta, so that alpha beta is delta D of P minus 1. I'm going to use it for alpha equals 1, but because I use alpha. So, and then I define two subsets of this thing. So the first one is what I call almost exponential. So this is going to be 1 minus alpha phi d rig, t to the k n rig psi equals alpha. And so this morally, so I told you that this case, this C corresponded to H1 Iwasawa of V. So these elements here correspond to the following. So they correspond to the element which are in the kernel of the exponential dual. So you have exponential dual map going from H1 of GFN. So Fn is just QP added the P to the nth root of unity with value in V tensor I. And this goes to field 0 of something. Well, this space generated by E1 and E2. Well, anyway, this is dual exponential map. Well, maybe I don't put it because this is not correct. So you have an dual exponential map going from H1, and these elements here correspond to things which are in the kernel. So in the kernel, for all n and I between 0 and k minus 1. And then you have something which, because I have no time, I am not going to define precisely, something called CE alpha, which is the same thing but in the image of the exponential map, exponential of Bloch-Kato. So the exponential goes from D de Rham to the H1. Okay, so you have these two things. And now what happens in the following? And so I'm not going to tell you how you prove these things, but why they explain that in one case you have locally algebraic vectors and in another case you don't have locally algebraic vectors. So what happens is the following. Is that, well, first you prove that W of C alpha E is C beta PE and vice versa. W of C PE alpha is equal to W is equal to C E beta. So this uses a lot the interpretation in terms of Iwasawa theory plus the antisymmetry of the pairing I defined. So that's where you use this fact. So that's the first thing. And the second thing is that, in fact, you have that C E alpha is equal to C PE alpha if de Rham. But it is not true at all if you are not de Rham. So if in the case, sorry, here you have he. In the case it is not de Rham, you have that CE alpha plus C PE alpha is equal to the whole of C rig if not the RAM. Okay, so this explains to you why you can find inside your big module something which is stable by W. In the case where you have the RAM, it's because of that. And in a case where you are not the RAM, then there is nothing which is stable. And maybe I just tell you where you can find your locally algebraic vectors now. So this implies that now if you are the RAM, so this implies that this t to the k n rig cross P1 is stable by GL2 of QP. So by which I mean things for which when you look at Z1 and Z2, they fall into this. And now you get some locally algebraic vectors in the following way. So you have this P star, well, maybe is, yeah, so maybe I remind you that you have this exact sequence. So here it was an dual. P an goes to 0. So you look at P star, P an star intersected with this thing to the k n rig cross P1. So this is inside, this is stable by GL2 of QP. And you can, well, I mean, so you mod out, I mean, by P an dual tensor delta D minus 1. So you take this and you mod out by that. And what you prove is that this is exactly the locally algebraic vectors in the dual of pi alg dual. So what you construct in this way is the contragradient of the locally algebraic vectors. You don't construct directly locally algebraic vectors, but you construct directly their contragradient. So I think I will stop here.